So let's have an application for a case when we can apply the single model. So here we have a company that wants to open a kiosk in a shopping mall, and there will be one sales agent working there. So obviously we have a single server here. It was given or estimated that requests would come at a rate of 15 per hour during peak periods. So it doesn't matter what's our period, as long as this will be consistent in all our calculations. So during a certain peak period, let's say 2 hours, 3 hours, whatever, this is the arrival rate. Okay, it's 15 per hour. Now, and it follows a Poisson distribution. Service duration follows an exponential distribution, and previous data told us that on average, we'll have a service time which is 3 minutes. Okay, so we need to determine a number of performance measures. But before doing that, let's establish the parameters of the model, meaning that let's find lambda, let's find mu. And for us, m is very clear that we have one agent, so m equal 1. Before you start solving any waiting line model, especially that we have a completely different models how to find the measures, make sure that you answer these three questions very with a great attention. What is arrival rate? What's the service rate? And is it single or multiple? It's very important. Once you do that, it's only a matter of plugging figures in the formulas that are given to us. So let's find the first one, lambda. What's lambda? Lambda was given to us very clearly in the second paragraph. It's 15 per hour. Okay, here we have to always pay attention to the time unit used. It's in hour, so make sure that the time unit for mu, okay, would be also in hour. Now we are given the service time to be 3 minutes. From that, I can find the service rate, right, which is equal to the inverse of service time, so 1/3. But I cannot leave it like that, because then it would be customers per minute, which does not comply with the time unit for lambda. So that's why I multiply that by 60 and I get 20 customers per hour. And now the time units match. Okay, this is very important. Once you do that correctly, then you should be good. So let's answer the other questions. So we found from the previous slides lambda and mu, okay, to be equal to 15 customers per hour and mu 20 customers per hour. And you can see here that I have already calculated lambda over mu, which is 0.75. Okay, this is lambda over mu. Why? As we discussed before, lambda over mu is a ratio that you see very often in different functions or different formulas. So it's better to find it in the beginning. So the first part, server utilization, this is rho. Rho is lambda over mu, and in this case m is 1, but we can always use this general formula, okay, where m is equal to 1 here. So it's simply equal to lambda over mu, which is our ratio, 0.75. Percent of time the sales agent will be idle. He will be idle when? Okay, he will be idle when he's not busy. So that's equal to 1 minus rho, right? So that's 0.25. 25% of the time he will be idle. The expected number of customers waiting to be served. What's that? Waiting to be served. That means they are not getting served. So which means they are waiting in line, which means this is LQ. LQ is given, this is a model specific formula. So here what I have used is a basic relationship, right? And here I just use a logic. And here I'm using a model specific formula, okay, which is lambda square mu minus lambda. Everything is given to us, so we get 2.25. Also, as discussed before, always give please a unit to your measure. Here we have 2.25 customers. Yes, it makes sense to leave it like that, because on average we have 2.25 customers waiting in line. Sometimes we have 2, sometimes we have 1, sometimes no one, sometimes 5. Okay, on average 2.25. Never round. Let's always keep 2 decimals. All right. Expected number of customers in the system. What's that? These are the people waiting in line plus those being served. So we can use the basic relationship, right? It's a basic relationship where we know relationship between LS and LQ. So here we go. LS, LQ plus lambda over mu, why lambda over mu? Because this is number of people being served at any point of time. Again, our famous ratio. So that's 3 customers. So we'll continue with this example. Now we need to find the average time a customer wait in line. This is what? This is WQ. WQ from the basic relationship also. Here I'm just showing you what I'm using to find this measure. So it's WQ over, WQ is LQ over lambda. That would be 0.15. 0.15 what? This time unit comes from the time unit which is here, lambda, okay, which is per hour. So that's why in hour. I like always to convert that into minutes because it makes more sense for me, or I can interpret it easily, okay, than 0.15 hour. Average time a customer will spend in the system. We know that the time it takes you in the system is the time that it takes you in the line plus the time of the service. We have already found that, and we already are given the service time, so it's easy for me to use the first formula, which is WS is WQ plus service time. Again, this comes from the basic relationship. It's not specific for any model. So that's 12 minutes. The probability of 0 customers in the system, all probability functions are model-specific formulas. So that's here, M. Okay, so that's P0, which is 1 minus lambda over mu. Again, our famous ratio, lambda over mu. Okay, so that's 1 minus 0.75 equals to 0.25. Okay, so you can notice that this is exactly the answer that we got for when we calculated the idle time. Of course, because this is a single server, the idle time is equal to P0 because he's idle only when there's no one in the facility. Finally, or in fact, we have one more coming, but in this slide, this is the last one. The probability that an arriving customer has to wait. All right, this is a nice one because it can you can use a logic here. I'm going to denote that by PW, probability of an arriving customer to wait. So PW. Think about that. You are arriving to that system where this is our system, and I know that is a single system. You are outside, you don't know what's inside. You are arriving. So here we go. You're wondering, in which case I'm going to wait. What do you think? You're going to wait if you arrive, and of course, if there's one person. So PW, okay, is equal to P1, which is there's one customer. So I have to wait. But this is not the only case when I will wait. What if one is being served and another guy who came before me is also waiting? I have to wait. So I have to add here plus P2, right? And you can see that I will have so many cases. So, and P3 and P4, right? So here we go. PW is equal to P1 plus P2 plus P3 plus what I wrote there. However, it would be really time consuming to find all these probabilities. Instead, look, what's still remaining? P1 is the case when I have one person. This is 2 person, 3 person, etc. All that. The only remaining case is when I don't have anyone. So that's why all these probabilities is equal to 1 minus the remaining case, or the probability of the remaining case. So that's 1 minus P0, which is equal to 0.25. So the probability that I will wait is 75%. Okay, I hope that that was clear for you. Okay, I kept the last or the hardest question at the end. It's not very hard, however, it needs some analysis before we can answer the question. Here the question is to find the probability of more than 3 waiting in line. So the first difficulty that we are facing here is, look, even if this question was what the probability of 3 customers waiting in line, this is not P3. It's not P3. Why? Because the probability given that I can denote it by P3, Pn, is number of customers in the system, remember? But here they are asking me about probability of people waiting in line. So what I have to do in order to be able to use the probability formulas provided to us, I have to convert that. Okay, I need to change this one, okay, in order to make it in a system. So I need to do a certain transformation. I will find an equivalent condition in terms of number of customers in the system. So you ask yourself this question. If we have 3 customers in line, how many are in the system? Okay, if we answer this question, then we can transform the probability statement into a statement that involves number of people waiting in the system, and then I can use the formulas. So here we go. This is this is our system, okay, and I have one server as given to us, in which case I can see 3 people waiting in line. Why they are waiting in line? Because the server is busy. Busy with whom? Busy with one more customer. So 3 in line means what? Means 4 in the system. Similarly, 4 in lines means 5 in the system, and so on. This is a relationship between number of people in line, number of people in the system. It's very logical, right? So now I can rewrite my probability statement and say that to find the probability of more than 3 in line, I'm going to convert that into system. So instead of line, I have system. So instead of writing here 3, it will be 4 in the system. And now I can treat that normally. But now, what do you think? In which case I have more than 4 in the system? More than 4 in system, that means I have 5, 6, 7. All these cases satisfy this condition. But again, I don't want to really go on in my calculations with maybe never ending. I don't know. It will end at some case, of course, when probability becomes very, very small. But why to do that when I can restrict my calculations to fewer? Okay, so instead of that, again, you ask yourself, what are the remaining events, or what are the remaining conditions that you're going to see in the system, so that you can find their calculation, their probabilities. So here we have 5, 6, 7, etc. Okay, the remaining are what? 4, 3, 2, 1, and 0. And that's why this is equal to 1 minus P0, P1, P2, P3, P4. That's very limited. That's it. I know that I will do only these calculations. Now P0, we got it before. It was 0.25. We need to find P1, P2, P3, P4 using the formula. And the formula is given to us as equal. Let me just erase that because it's blocking. Okay, so the formula is given as Pn is our ratio again, lambda over mu to the power n times P0. So it's equal to, the ratio is already established, 0.75 to the power n times 0.25, okay, which is P0. So P1, I just replace n with 1, I will get this. P2, I will get that. P3, and P4. Okay, now I plug these values in the probability statement, and here we go. This is our final answer. So we have 23.73% probability that we'll see more than 4 people in the system. Okay, so I hope that this problem was clear enough for you. By the way, it includes all kinds of questions that you can ever encounter. So if you understand very well the answers or the solutions, you are very ready.